Morning, Nguyen. We wait for a couple of minutes before we start. Thank you. Morning, Daniel. Morning, Flynn. 2 more minutes and then we start. Okay, good morning again. Shahin is here, second week, and again, for the entire second week, we will be summarizing some of the concepts you are already familiar with. So last week, what we did was we found how forces can be combined together as a vector. So adding vectors is not like adding numbers. When you are adding numbers, 2 plus 2 is equal 4. But when you are adding two vectors, 2 and 2, it depends what are the angle between the forces. So you can't answer that question unless you solve the summation in a vector form. So the second family of this, the second member of this family, the first member was force. All right. So let me just make a simple chart for you. That is to outline that we have started with the vectors. So what is the first member of this family? The first member is position vector. The second member is force. And the third member that we are going to discuss this week, that is called moment. So these three members, they belong to the big family of the vectors. And what it means is, if you want to combine position vectors, you have to do it in a vector way. If you want to combine forces, you have to combine or multiply them in a vector way. And the very same thing applies to the moment. So first, we need to remember what a moment means, and that's how we start. Okay. Moment is simply the tendency of a system to rotate. So when we are talking about a moment, this is not either there are one force or two force, they are causing a rotation, And then this is not all about the force or the resultant. So this is the resultant. Also, there is a point of rotation. So this is the point of rotation. Point of rotation. So moment is the tendency of the system to rotate. So in this case, that resultant is making my system to rotate counterclockwise. Everything comfortable with that? Okay, let me ask a question. If you have to apply a force to rotate, this is a spanner, you want to rotate the spanner, or you want to apply a rotation here. Would it be better to do this at this angle, or at this angle, or at this angle? Which one is more important? This is 1, 2, 3. Which way of applying the force is more effective? If you want to make a rotation with respect to the point, the most effective way is when your force is normal to this line. So let me find out this R. That is the position vector of the rotation. R is the position vector of rotation. How do I find it? From the point of rotation, I have to connect to the end of the vector, to the start of the vector. All right. So let me summarize. R is the position vector of the rotation. F is the resultant of the rotation. The most effective way of applying this, if you want to have 100% effective, that should be normal to this one. So what happens if this is not normal? If this is not normal, only a portion of that force would be consumed for the rotation, which is the normal. And the other component, which is align the position vector, that doesn't make any rotation. That is wasted. This is like you are pushing a wall, you cannot move the wall. So this is a wardrobe and you want to slide it. If you apply this force like that, this is effective. You would slide this in this direction. But if you apply your force like that, this is not going to slide. This would be penetrated here. So this is not effective. Very same way here. If you want to rotate, normal to that line is effective to rotate. If you apply the force aligned with that position vector, that won't make any rotation because this line after extension passes through that point of rotation. Okay, hopefully everyone followed what I tried to explain. And now the vector, I mentioned the third member of this family is moment. Okay, so moment is a vector, but is an easy way of calculating moment, is a difficult way of calculating the moment. The easy way is if the moments are parallel, we can pretend they are like a scalar and adding them together. That's the first thing we do. In the first thing, if I have all the forces inside a plane, so the forces here are inside the plane. This is the plane of xy, right? If my forces and the position vector are making a plane, like what they do here, I don't have to worry about the moment to be a vector. I know that this vector is normal to the plane, so I can use my right hand to say the moment about point A that is projecting out of the plane. So this is normal to the plane. This is a vector, but for now the magnitude is most important. The magnitude is force multiplied by shortest distance. Why shortest distance? Why I don't say F multiplied by H? Okay, so this is a position vector, isn't it? I connected from point of rotation to the end of the vector. This is a position vector. But if I want to do it this way, I have to do this in a vector fashion. But because I want to give you the easiest way of doing that, that's a scalar treatment of the moment. The moment can be treated as a scalar if all moments are parallel. We can add them like numbers. If they are not parallel, we have to deal with them in a three-dimensional sense as a vector. So generally speaking, MA is F as a vector cross product by D as a vector. But that we postpone that usage to later on. We start with the most simple case when we only are worried about the magnitude of the moment, which is the magnitude of the force multiplied by the magnitude of the shortest distance. So the shortest distance between point A and F, you have to make line of action for the force. This is the line of action. I call this line of action. And then from point of rotation, I make a normal to the line of action. And that distance is what I should use here. I never use F times H. That is wrong. I don't use F times B. That is wrong. The correct one is F times D. And what is D? D is the shortest distance between point of rotation and line of action of the force itself. That I do all of that because the moment want to treat that as a scalar, not as a vector. Once you fully understand that, we move into the vector analysis. So how can I do this? First, let me explain it this way. Okay, three scenarios. Scenario one, I'm making from point of rotation to beginning of the force. But wait, where is the beginning of the force? Is this here? Or what if I shift the force along the line of action? Is this the same effect? If I transfer this one along the line of action and bring this here, wouldn't it be the same force? Yes or no? Porty, do you reckon I can transfer the force along the line of action? Is this permissible or this is wrong? It is right or wrong? Porty? Nguyen, is this okay if I move the force along the line of action? In another word, my question is, if I transfer this force along this line, bring it here, is this going to make the same rotational effect as it was here? Are these two the same? Yes or no? The answer is yes. Yes, thank you, Porty. We are allowed to move a vector along the line of action. This is like two groups of people are taking a rope, and some group are pulling this from here, some group here. So these are balanced. If these people, instead of grabbing this part of the rope, they're grabbing this part and apply the same force, still the system is under equilibrium. So that is the first thing we learn. It is okay to shift a vector as long as the line of action doesn't move. All right? So in another way, three scenarios here. Scenario one, when the force is located at B. This is, I call this, for example, S, right? So I brought that force, the very same force, starting at here, right? The same thing. The third scenario, this is scenario two. Scenario number three, that is, I bring the same force to point C. In all three cases, I'm moving the same force along the line of action. So in scenario one, I have to connect from A to the beginning of the force. And then in the second one, I have to connect from the point of rotation to the beginning of this one. In the third scenario, I connect from, so I have three position vector. Position vector one, position number one, that is H, the position vector. In scenario number two, the position vector is D. And in the third scenario, the position vector is B. Which one should I use? If I want to go with the scalar, rotation about A. So a scalar, that is the shortest distance. Who can tell me which one of these three vectors is the shortest distance? Is this H? Is this D? Is this B? Which one is the shortest distance? Flynn, which one is the shortest? Darcy, which one is the shortest? Is this H, D, or B? Daniel, Abdullah, anyone? Nguyen, Porty. Okay, both correct. Flynn and Darcy both correct. The shortest distance is D. So if you want to find that moment in a scalar, if you want to find this as a scalar, it has to be the shortest distance. And the shortest distance is D. So that is the magnitude of the force multiplied by D. It is wrong if I want to write as a scalar, MA is not equal to F times H. It's not equal to F times B, because neither B, neither D are not the shortest distance. So from now on, whenever we want to find the force, um, the rotation in a scalar fashion, we need to find the shortest distance. And then that I can easily verify for you, right? So at this instance, let me break this force into two components, one normal and one which is parallel to H. The one which is parallel to H, that doesn't make any rotation because it passes from point of rotation. And that one, this is what? That is F multiplied by cos theta. And this is like H multiplied by cos theta, that is D. H multiplied by cos theta, that is equal to D. So this is like I'm talking F multiplied by D. The very same thing in the third scenario. I break the forces into two components, Fx, Fy. Fx is moving, is passing through A, doesn't make any rotation. Fy is normal, that makes a rotation. But Fy is what? Fy is has a cos component, cos of this angle, and that angle is B cos theta is equal to D. So therefore, again, in the third scenario, I'm finding the rotation with F multiplied by D. Don't worry if you didn't quite understand this one. I give you some examples soon, and we would discover that from there. Let's try this exercise. I want everyone to grab a piece of paper and try to find the rotational effect of the force with respect to point O. So let me help you with that part. How do I find rotational effect of F with respect to the O? I would call this rotation about O. And in this case, the forces and position vectors are in this one plane. This is a two-dimensional case. In the two-dimensional case, we calculate only the magnitude of the moment, and therefore this is a scalar. This is not a vector. So one way of doing that is I can find the line of action for that one. So this is the line of action. And from point of rotation, I find the shortest distance between point of rotation and the line of action, which is I have to draw a normal to that. So that distance is, this is equal to 400 times h. No problem. That's one way. But the problem is to find h, I have to solve this triangle. To solve this triangle, how do I solve this triangle? Well, I need to do a bit of trigonometry to find that angle, and then to find this angle, and then to find that angle here. And then in that triangle, I know the hypotenuse. The hypotenuse is root 0.2 squared plus 0.4 squared. But there is an easy way of doing that. If I want to skip the trigonometry, let me project this force into two components. That component and this component here. That is 400 cos 30, and this one is 400 sine 30. Now, MO is equal to, so that doesn't exist anymore because I broke that into two components. So MO is the rotation due to 400 cos 30. And what is the shortest distance between these force and here? The shortest distance is I draw a line of action, and the shortest distance is from here to there, which is equal to 0.4. And what is the rotation due to the second one? The second one is 400 sine 30. And what is the arm of rotation? What is the shortest distance? I find the line of action for that. And then from point of rotation, I make a normal to this one. And that arm of rotation is 0.2. But one more thing. Should I add these two vectors together or subtract them? All right, let's see if that is made of a cardboard and I pin the cardboard to the wall at this point, and then I try to rotate the cardboard by this force. Then my cardboard or the poster, this is going to rotate clockwise, isn't it? Now, what about this force? If the very same poster is pinned to the wall and is free to rotate here, then I exert this force, my poster would rotate counterclockwise. So counterclockwise, I assume this is positive, that is positive, and sorry, this is positive, and the clockwise, I take this as a negative, that would be negative. So I have to add these two terms together. If my result is positive, that would be the entire rotation being counterclockwise. If that is negative, the entire rotation is counter. And in this case, it's not difficult to understand that the entire rotation will be clockwise. So I know that the result, whatever that is going to be a negative number. Because just by looking here, this force is making my poster about that point to rotate clockwise. All right. Is this clear? Anyone want me to explain again? Did you follow my solution? Okay, Nguyen, you want me to explain again? All right. Thank you. Let's do that again. All right. So two possible solutions. The first solution is rotation of the force 400 with respect to the O. I need to have the line of action. The line of action, I need to extend this force. And then what is the shortest distance between that green line and the point of rotation? The shortest distance is here, isn't it? Do you agree with that, Nguyen? That the shortest distance here is h multiplied by f. Yes, and is this going to be clockwise or counterclockwise, Nguyen? With this one, is this going to be clockwise or counterclockwise? If this is a poster which is only fixed to the wall by a pin, by a tack pin here, and then I apply this force. This poster, this is going to rotate counterclockwise, isn't it? Clockwise, isn't it? So I make it contract. Clockwise is negative, counterclockwise is positive. So I know that this one would be negative rotation. But to find h is not simple because I have to do some angle calculation and trigonometry. So instead, I decide to do a simple way. The simple way is, let me break this force into two components, component 1, component 2. And then I broke that to the component. This force doesn't exist. Yeah, these are conventions. These are standards. These are assumptions. We assume that if my system under the force would like to rotate in a clockwise direction. So here, that's a poster. So this is a poster of a person. You want to fix it to the wall, and then Just by mistake, Nguyen, you put one tach pin here. So this is point O. So this poster can either rotate in this direction and that direction. Do you follow that, Nguyen? Because it's only fixed to the wall by one pin, point of rotation. Does that make sense, Nguyen? Okay. Now, if my system, if I apply a force like this one, that would make my poster to rotate this way. And this is counterclockwise, anti-clockwise, counterclockwise. If I apply a force like that, that would rotate in this direction. And this is how a clock rotates. We call this clockwise. So that is just a convention. This is just an assumption. Whenever my system rotates opposite to the clock, we call this CCW, we call this positive. And whenever it rotates in clock direction, we call this clockwise and take that as negative. That convention is to help us because these two forces are canceling each other. And this is the point of doing the vectors in a scalar fashion. They are parallel, but they might have opposite sense. One might rotate clockwise, one might rotate counterclockwise. So we make that convention to allow they're being added or subtracted from each other. Any more question, Nguyen? Is that clear? Should I go on? So far, so good? Okay. Now, these two forces, Nguyen, are what? These two forces are 400 cos 30, and this one is 400 sine 30. And then let's just cross this one. That doesn't exist anymore. Now my system is under rotation with two forces. This one tends to rotate my system in a counterclockwise, which is positive. Imagine this is a poster being fixed to the wall in this point by a pin. It can rotate positive. This point with respect to here, does this make a positive or negative rotation? Nguyen? 400 cos 30, does it make positive rotation or negative rotation? Clockwise or counterclockwise? Yes, that's negative, right? So, and then how do I, this is M1, this is M2. M1, let's find M1. M1, which is negative, that is 400 cos 30. And what is the arm of rotation? Arm of rotation is the shortest distance between this vector and the point of rotation. That is from this point to this point. That is 0.4. And what is the rotation due to the horizontal force? M2. M2 is positive, and that is force 400 sine 30, sine theta. And what is the shortest distance between this force and the point of rotation? The shortest distance is 0.2. So that has to be multiplied by 0.2. And then the total rotation is M1 plus M2. If you calculate this number, the result would be something negative. I'm lazy, I leave that for you to do, but we know that this is going to rotate in clockwise. So, and this is just verified by adding these two numbers, you get a negative number. That negative number tells you the resultant of M1 plus M2 is in the clockwise. Are you happy with it now, or did I miss any explanation? All right, thank you. Let's move on. So these are, yes, they have decided to break the force into two components. And we see that the horizontal, it has the shortest distance with O of 0.2. The vertical has the shortest distance of 0.4 with O. And that is how you break that into two torques, one of them being negative, one is positive. The positive is the one which is opposite to the clock. The negative is the one which rotates along the clock direction. And eventually you get a negative number. Negative number is the clockwise direction. And if you want to write this as a vector, we know that this vector is normal to the plane. So that is the magnitude. This is the magnitude of the force. This is the magnitude multiplied by the unit vector. The unit vector, this is y, unit vector of j. This is x, unit vector of I. And if this is x, y, the z or k, that would be normal to this plane. So as a vector, that is the magnitude multiplied by the unit vector. That's as a vector. The second method is when you draw the line of action for this one, and then the shortest distance between this vector and here, you have to draw a normal. So that means you have to calculate this length here. So that requires some trigonometry. Or you could just write the position vector as a vector and the force vector as a vector. So we know that from energy and motion that m as a vector is r cross product by f. That is the second method. So what is r? R is the position vector from here to here. How do I write the position vector? I want to go from point O to this point. First, I draw negative j 0.2, negative 0.2 j, and then positive 0.4. That is the position vector. What about the f? F is negative this component j, positive this component I, positive, negative. And then you do the cross product. The cross product, yes, you do the cross product. I know that every vector cross product by itself is 0. If that is cross product by a unit vector normal to it, that is unit. So that you do, or you do the matrix method to do the calculation, and that gives you the same answer. Now, listen carefully here. Here we've got a plumber. The plumber is trying to rotate a pipe. So here you have a pipe, and this person is trying to rotate this pipe in a direction shown with a blue arrow. And the best way, the smart way of doing that is if they hold their hand by applying this force normal to this spanner. It would be dumb if the spanner, if they apply this force this direction. Why this is dumb? If they pull it this way or push it this way, it only going to bend the pipe. The force would pass through the point of rotation and it won't cause any rotation. The best way of rotating that is you apply this force normal to the position vector. Position vector is from point of rotation to one point belonging to the vector. So this is one point, that is one point. You can construct the position vector in any way you want. But if you want to do it in a simple scalar way, we multiply the magnitude of the force by magnitude of the shortest distance. What is the shortest distance between point of rotation and that vector? The shortest distance is you have to extend the vector and then draw a normal from point of rotation to the line of action or extension of the force. That is dy. So in a scalar fashion, MOZ scalar fashion, that is fx multiplied by dy. That's a scalar fashion. If you want to do it in a vector way, yes, you can choose whatever position vector you want, write it as a vector, write this force as a vector, and then cross product them together. That we do it later, but for now, the early part of the lecture today, we go through the scalar form. A scalar form requires the magnitude of force multiplied by the shortest distance. Shortest distance, that is when you extend the force and then draw a normal from the point of rotation to the line of action. All right, now the very same plumber is trying to rotate the pipe, but then mistakenly they applied the force parallel to z-axis. about point O. So what's going to happen here? Here, the pipe would not rotate. The pipe would bend, right? So if I apply something like that, the chances are my pipe would bend like so, right? So this is, if I rotate it like that, instead of having the pipe rotated, that would rotate about the x-axis. This is not the best way of applying the force. If you want to rotate the pipe, that's the wrong way of, wrong direction of the force. Okay, so what if I pull the spanner? If I pull it, that won't cause any rotation. It would cause a translation, right? So therefore, a force like this cannot make any rotational effect. So in another words, we say that, look, because this force is passing, if I extend that, that would pass through here. What is the shortest distance between point O and the force? Who can tell me in this diagram, what is the shortest distance? Darcy, what is the shortest distance in this case? Daniel, what is the shortest distance here? Flynn, Abdullah, 40, anyone? In this diagram, can you tell me what is the shortest distance of the force and the point of rotation? Come on, this is not very difficult. The shortest distance is 0. Why? Because the force is passing through point O. If I draw a normal from O to that extended line or line of action, the length of that radius is 0. So the torque due to this one, that is Fy, which is not 0, multiplied by 0. So that is 0. 0 rotation. This force would not cause any rotation here. Everyone follows the explanation? Yes, no? Just give me a feedback, please. Hello, either you follow or you not. Just give me a feedback. Come on, I'm waiting. Yes, yes, I explain again. I explain again. Thank you, Porty, for being honest. Look, here you are pulling, forget about the mathematics, forget about the vectors, everything, Porty. If you pull a pipe with that wrench, is this going to cause a rotation, Porty? Yes or no? That would translate the pipe, but doesn't cause the rotation, right? Can you visualize that, Porty? All right, so now let's say that in a mathematical term. In a mathematical term, what did I say? I said rotation of the system due to F, the rotation of the system due to F. That is the magnitude of the force, which is Fy, multiplied by shortest distance of the force by the point of rotation. But the point of rotation is the origin of the coordinate system. And what is the distance between here? The shortest distance. Look, here is a line, here's a point. 40. What is the shortest distance between point O and line AA? Do you remember that from mathematics? Is this going to be this one, or this is this one, or is this going to be shortest distance is this one? Which one is the shortest? When you draw a normal from a point to a line, that is the shortest distance. You remember that, Porty? All right, exactly that's what we did here. Here, I want to find the shortest distance between O and this force. I extend that, this is the line, but my point is not outside the line. My point is here. If I draw a normal from here to line, how long is it? This is 0. right? So that is 0. Because my line passes through the point of rotation, the distance is 0. So that is multiplied by 0. That is 0. So no rotation taking place. So that's what you told me. You told me if someone is pulling this pipe, it won't rotate. So that's mathematical proof. Magnitude of the force multiplied by the shortest distance. Shortest distance here is 0. Okay, thank you, Porty. All right, what about here? Is this a smart way of doing that? Yes, this is a smart, because all this force is being consumed to rotate. In this case, the shortest distance between this force and that here, you have to draw this is line extension. You draw a normal from the point of rotation to the vector, and this distance is equal to this distance. So here, the rotation MOZ, that is Fx multiplied by dy. That is not 0, that is maximum. So why I say maximum? Because all force is being consumed to make a rotational effect. Imagine that if I had the force acted at an angle, this was not very effective, because then I would have projected the force into Fx, Fy, and only Fy, which is a small part of the total F, is consumed to make a rotation. This part is passing through the point of rotation, won't make any rotation. So in conclusion, when you apply a force at an angle, only the component which is normal to this shortest distance, that is causing the rotation. All right, now we want to jump into the three-dimensional case. In a three-dimensional case, how do we know if the bending, we know that the moment is normal to the point of rotation, but the question is this projecting out of the plane or is this projecting in the plane? We are using a rule which is called the right-hand rule. In the right-hand rule, you hold your right hand with 4 fingers following the direction of the rotation, and then your thumb shows the direction of the moment. In this case, for the blue vector shown, the blue moment, your thumb is showing the upward direction. So this way, the force shortest distance of D are making a rotation perpendicular to the page upward. That's sense of rotation. And the unit is Newton meter. Now, what if I have a system of forces which are making a rotation? So one way of that is, if I want to find the total rotation effect, I have to do the total rotation is MRO. This is the rotation due to the F1 plus rotation due to the F2 plus rotation due to F3. And these are F1 D1, which is in a positive Z. F2, is this positive or negative rotation? Yes, that is positive, because your thumb would show up, that is plus F2 D2. And the third one is also positive, that is plus F3 D3. If hypothetically I had this one directed this way, then I should have changed this sign to negative, because then F2 using the right hand rule is pointing down. That's the negative direction. So far, so good. So is there another way of doing this? Yes, a more effective way is, before I go to the rotation, I could combine F1, F2, F3 into one single force. I call this a resultant force. So that resultant force, whatever that is, I need to find this distance, shortest distance. That is I call D. So then MRO is the resultant of the forces multiplied by the shortest distance of the resultant to the point of rotation, which is D. So mathematically, that is how we explain that. But don't worry about the mathematics. We are going to see this shortly in an exercise. All right, now you get into your first step of analyzing the effect of the forces. So this is a building, 2 walls. You have one structural member or a beam which is positioned horizontally at point A and B. So here this is horizontal. One end is sitting at A, one end is sitting at B. If you apply a point here, if you apply a force F here, is this making my system to rotate clockwise or counterclockwise? Anyone can answer the question. F, is this rotating my system clockwise or counterclockwise? Daniel, F, is this rotating my system clockwise or counterclockwise? Darcy, Nguyen, Horty, Abdullah. All right, to answer this question, all right, yes, Darcy is suggesting this is going to be counterclockwise, but in reality, we have to find 2 rotational effects, one respect to the A, one respect to the B. And then the thing is, the reaction from here is going to cancel that force over here. But to answer this question, F is making a negative rotation about point A, and it makes a positive rotation about point B. So to answer this question, you have to add these 2 effects together and see whether the resultant is positive or negative. Okay? So here we have 2 points of rotation, 2 hypothetical points of rotation. But then in a case like this, the system doesn't rotate, the system doesn't translate. So this is what we call a state of equilibrium. A state of equilibrium that is stationary. Every building should be stationary. If the building or if a bridge is not stationary, that means it collapses. Okay? So in this subject, every complex structure that we analyze, the total rotation should be equal to 0. The net rotation should be equal to 0. And that would ensure that my system does not rotate clockwise, does not rotate counterclockwise. So this is a very important condition. From now on, when we want to say that the system is stable, when we want to say the system doesn't rotate, we say the net rotation is equal to 0. Yes, you can find out the rotation of the F with respect to the A. You can investigate the rotation of F with respect to the B. But for the total system, you have to put all the rotational systems together and set them equal to 0. Anyone followed my discussion or conclusion? All right, let's do some practice. So here we have 2 rotational effects. FDA, that is force F, shortest distance. This is the line of action. You draw from point of rotation to here. That's the shortest distance, dA. So that's FDA. How do I find the rotation of F with respect to the B? Extend that line of action, draw a normal from point of rotation to here. That's the shortest distance, dB. So the second rotational effect is here. But the first rotational effect is negative. The second rotational effect is positive. If I want to combine them together, I have to take the second one away from the first one. All right, so this exercise is very important. I want to give you 2 minutes. Please grab a piece of paper and we try to solve all the sections together. Please, in 2 minutes, we're trying to solve that all together. That's very important. If you understand this exercise, everything we said so far, you would apply your knowledge to solving this problem. So therefore, it's extremely important that you follow every solution in this slide. Otherwise, I keep repeating that until everyone is 100% happy. Okay, 2 minutes and then we get started. All right, let's get started with the first one. Who can help me with finding this one? I want to find the rotational effect of the force with respect to point O. So I want to find MO. That is, in a scalar calculation, is the magnitude of the force multiplied by the shortest distance between the line of action of the force and point. What is the shortest distance? Nguyen, what is the shortest distance? Yes, the shortest distance is 2. And is this outcome positive or negative? 40. Is this outcome positive? Yes, that is negative because that's counterclock. This is clockwise, that's negative. Thank you for that. This is minus 200. And what is the unit? Flynn, what is the unit? That's Newton meter. Yeah, thank you, Flynn. Let's go to the next one. So again, we want to find rotational effect of 50 Newton with respect to the O. So rotational effect with respect to O in a scalar way, that is the magnitude of the force 50 Newton. And what is the shortest distance? Is this 0.75 or is this 2 or this is something else? Darcy, what is the shortest distance of this force with respect to O? Daniel, what is? Yes, well done, Darcy. So according to Darcy, I just extend that line and then I draw a normal from here to here. And that normal, guess what? How long is it? This is 0.75. So that is multiplied by 0.75. And Flynn, is this going to be clockwise or counterclockwise rotation? Yes, that is clockwise. So therefore, that's going to be negative. Everyone happy? Can we move on? Thank you, Forty. Let's move on to the next one. The third one is a little bit tricky. So I'll be happy to see if anyone can do the third one for the class. So what is the rotational effect of 40 Newton with respect to the O? That is equal to the magnitude of the force multiplied by what is the shortest distance between 40 and O? So I need to extend this one. This is line of action. And then from point of rotation, I make it normal to here. And that is the distance. This is the shortest distance. So the shortest distance is equal to two portions, this portion and that portion. So that is 4 meter plus 2 times cos 30. And is this clockwise or counterclockwise? Abdullah, is this rotating clockwise or counterclockwise? Nguyen, is this clockwise or counterclockwise? Positive, negative? Yes, that is counterclockwise, correct. Counterclockwise, so therefore the outcome is negative. All right, next one. The fourth one. The rotational effect of 60 Newton with respect to point O, that is equal to 60 Newton multiplied by shortest distance. So who can tell me what is the shortest distance? I extend this force, that's the line of action. And then from point of rotation, yes, that is sine 45. Thank you, Nguyen. That is sine, or 1 times sine 35. And is this rotating clockwise? Does this rotate clockwise or positive or negative? Yes, that is counterclockwise. Therefore, this is positive. Well done, Nguyen. Everyone happy? Can we move on? Any objections? I assume everyone is happy. Thank you, Porty. Let's go to the next one. Okay, the last one is a little bit tricky, but I trust that everyone should be able to do it. Rotational effect of 7 kilonewton with respect to the O. That is 7 kilonewton. And what is the shortest distance between this force and point O? Is this one? Yes, well done, Nguyen. And why this is 3? Because you extend that one. And from here to here, the normal, that is not 4, this is not 1, this is not 2. That is 4, take away 1, which is 3. And is this positive or negative rotation? Yes, that is positive because that would rotate counterclockwise. And the unit is, in this case, the unit is kilonewton meter. That is the unit. Positive kilonewton meter. All right. So let's have a look at the solutions. So the solutions, nothing new, you know all of that. We discussed that in the class. Okay, let's try something different. So this example, can you find the rotational effect with respect to A, B, C, D? So again, we're doing this all together. Rotational effect, first respect to A, MA. We start with rotational effect with respect to point of rotation A. So in this case, that frame, this picture, is fixed to the wall only at this point. So if you apply this force, that would rotate clockwise, isn't it? That is 800. And what is the shortest distance with respect to the A? 2.5, isn't it? Yes, that's times 2.5. And the direction is negative. That is a clockwise. What is rotational effect with respect to point B? That is again 800. What is the shortest distance? Darcy? Daniel, what is the shortest distance with respect to the B? So thank you, Party, that's 1.5. And again, that is going to be negative. The next one is MC. So that I want Abdullah to tell me with this one is 800 times what? What is the shortest distance of 800 and point C? Or maybe Daniel, Darcy, Flynn, can you tell me what is the shortest distance with respect to point C? Nguyen Porti. Yes, thank you, Flynn. Well done, Flynn. That is 0. So no rotation with respect to the C because this force is passing through C. So conclusion, when a force passes through a point, the rotation is 0. It won't cause any rotation. Thank you, Flynn, for that. And the last one is rotation with respect to point D. That is 800 multiplied. What is the shortest distance with respect to the D? Thank you, Porty, is 0.5. And is this positive or negative? Yes, thank you. Well done. That is positive. All right. Everyone happy with this solution? Can we move on? So here you have the detailed solution for that. Next exercise. In this exercise, we have how many forces? 1, 2, 3, 4. 4 forces. And we want to find the combined rotational effect. All right. So let's call this, label this one F1, this one F2, this one F3, and this one F4, right? So here, the total rotational effect, that is rotational effects of 1, rotational effects of 2, and all of these are with respect to point O, right? Rotational effect of 3, rotational effect of 4. And what is rotational effect of 1? M1, that is 50. The shortest distance between 50 and point O, that is 2. And is this positive rotation or negative rotation? That is a negative rotation. The second one, F2, Nguyen, F2, what is the 60 multiplied by what? Darcy, with the second one, what is the, yes, thank you, Nguyen, that is 0. And what about F3, M3? That is 20 multiplied by, what is the shortest distance? Daniel, sine 30 multiplied by 3. Thank you, Darcy. Sine, this is, yeah, this is 3 times sine 30. Because you have to project this line by sine 30, that's the shortest distance. This is 3 times sine 30. And is this positive or negative? M3. That is positive, counterclockwise. And finally, M4. M4 is equal to 40. What is the shortest distance between F4 and O? That is 2 plus 2 plus 3 cos 30. Okay, and then finally F4, does that make a positive rotation or negative rotation? Negative, right? So eventually you add all these together, minus, plus, plus, minus, and the total would be like so. Any question? Is that all clear? Can we move on? Okay, no question. Let's go on. Now that we know how to find the coplanar forces, coplanar means all forces are in one single plane. So coplanar forces, the moment can be calculated in a scalar fashion. But if the forces are not coplanar, the way we do it, this is the vector way. The vector way means M as a vector is the position vector multiplied by the force vector. And this is a cross product. So we remember from energy and motion or calculus high school what the cross product is. Okay? But then the question is, that is the point of rotation. This is the force. So here is my question. I can define the position in taking one point here, I call this B, one point here, I call this C, one point here, I call this D. So if I take a point on a vector as B, my position vector would be RB. If I connect from point of rotation to C, I call this RC. This one I call this RA. Then this one I call this RD. So the question, is this equal to RA times F? Is this RB times F or RC times F or RD times F? Which one is correct? That's a very important question. So I took 4 points. All 4 points are sitting on the vector. And then I constructed the position vector from point of rotation to that point. And then now my question is, which one is a better or the correct vector of moment? All right, so this is a difficult question. Let me answer that, but listen carefully. Okay, Nguyen suggests RB should be, RB is the shortest one, is it? Look, the shortest is only when you want to avoid the vector. When you are not avoiding the vector, position vector could be any of these selections. Depending on the problem, which one you have data for, you have measurement for. So when you are doing the vector cross product, it doesn't matter your position vector is which one. It could be RB, could be RC, RA, RD, and all of these would give you the same answer. The same answer is you pass a plane through these force and these vectors and normal to this plane. So this is normal to that plane, right? So that is the outcome. everyone heard what I said? So this is the contrast between finding a moment by vector, finding a vector by a scalar. When do we do the scalar? That is when all the forces are coplanar. The forces are coplanar. So if I want to do the scalar calculation, I need to find the shortest distance. That's all I have to do. But if I don't want to find the shortest distance, or if the forces are not on the same plane, I simply take the approach of a position vector cross product by the force vector, and that cross product gives me the answer no matter which one of these position vectors I choose. And here I give you examples. All right. So here, if the position vector is making an angle with the force of theta, and then this is a simple coplanar forces. So to find out the shortest distance is what? The shortest distance is r sine theta. R sine theta, that's the shortest distance. This is the arm of rotation. So arm of rotation, which is d multiplied by f, fd. That's a scalar, right? Very same thing that we said in a scalar fashion. No matter what theta, you always can calculate that one. This is still a vector fashion, but you do need to know the angle between the selected position vector and that one. If that angle is 90 degrees, what is sine 90? Sine 90 is 1. All right? So if I take an r, which is normal, that's the shortest distance, r star. So that is what we did so far without doing to the vectors. All right, so that is explaining what I just told you. If you are happy to do the moment calculation by vectors, it doesn't matter which position vector you choose, as long as one point of the position vector is the point of rotation, the second point is another point on the vector or located on the line of action. So that is the line of action. From here to here, that is the line of action, extension of the force. Any point here, A, B, C, even E, G, any point you get. So you can construct a position vector, and then that's R E times F. The same thing. So all these giving you the same answer. And how do we calculate that? Okay, how do we calculate the scalar, the vector product? The calculation is you have to construct a determinant, 3 by 3 determinant. The first row is ijk. The second row is the xy component of the position. And the last row is the component of the force vector. So if you extend that determinant, you end up with this relationship. This relationship is a little bit difficult to memorize, but I suggest in the exam, you use this formula. Why? Why do I say that? Because exam is the open book. And if you have access to this formula, that formula, all the signs are being decided for you and you don't have to worry about the signs. But if you do the determinant, the chances are you would confuse with the signs. Because every row and column you extend, you have to switch between the positive one, minus one. So I suggest in the exam, you use this formula because all the signs are there. Exam is the open book and you can access to this formula. Questions? All right, what if I have a number of different forces? All right, no problem. Every individual force is making a separate rotation. That is the rotation due to the F1, rotation due to F2, rotation due to F3. All you have to do is, these are vectors. You find them one by one. Each one of them requires a determinant, 3 by 3 determinant. and eventually all the three results, you add them together. So here I have a power post which is secured to the ground by a cable. We want to find the rotational effect of this force with respect to point A. How do we do that? All right. So one way is doing a scalar. If I want to do the scalar, from the point of rotation, I have to make a normal to this one, and that is RD. That's the shortest distance. So if I want to do this scalar, the magnitude of the rotation with respect to the A, that is RD multiplied by F. If I want to do this as a vector, I do RAC cross product by F. Or I can do RAB cross product by F. So these would give the same magnitude as the first one. All right, let's do this exercise together. We are short in time. I think I have to get this myself immediately, but let me know if you are left behind at any stage. I'm happy to explain that if you need. Okay, what is the rotational effect with respect to point A? Rotational effect with respect to the A. So because this is a three-dimensional problem, it's best to solve this by three-dimensional, by a vector, not by a scalar. All I have to do is I need to have force as a vector, and I need to have one position vector. So who can help me with the position vector of AB? From last week, we remember that to go from A to B, I simply go, well, AB. I want to go from A to B, 1 meter along positive X, 2 meter or 3 meter along the positive J, and 2 meter in positive K. So that is I plus 3J plus 2K. All right, so that's it. How about F? How can I write F? I know F is, magnitude of F is 60 Newton, and then this has to be multiplied by the unit vector of F. So what is unit vector of F? Unit vector of F is the same as unit vector of CB. You remember from last week? If not, just go back and read, listen to the recorded lecture or slides. So I want to find unit vector of CB. So to find that, first I need to find CB as a vector. So CB as a vector, that is 3 meter in the positive I, 4 meter, sorry, I'm going to go from C to B. C to B, I move 2 meter in negative I, and then I go 1 meter in negative J, and finally I go 2 meter in the positive K. And the magnitude of CB is root of 4 plus 1 plus 4, which is equal to 3. So therefore, the unit vector of CB is C itself divided by its magnitude. That is minus 2/3 I minus 1/3 J plus 2/3 K. And then all I have to do is multiply 60 by that unit vector. Questions? So this session is being recorded. If you need, you can always come back and watch this. If you have question, don't be shy. Ask me. I'm happy to explain again. Otherwise, I assume that you followed and we pass on the next question. No questions? Let's move on. So the very same problem. Okay, now that we have both components calculated, we want to find m. So m is equal to ijk, and then the component of r goes here. R, the components are 1, 3, 2, and the components of the f are minus 40, minus 20j, plus 40k. So this is minus 40, minus 20, plus 40. And that you can work out. And here we have the solution for that. Minus 40, minus 20, 40, the same. Next example. All right. Rotational effect with respect to O. That is M1 plus M2 plus M3. Okay. What is M1? M1, I can do this by taking OA multiplied by F1, and OA is what? OA is 0I plus 5J plus 0K. So this is IJK 0, 5, 0, and F1 is minus 60 plus 40 plus 20. Okay, I know that this rotation is the magnitude of the F multiplied by the shortest distance. And yeah, either way, here you can calculate M1. What about M2? M2, I know that this is 0 because F2 is passing through O. That is equal to 0. And what about M3? That is the position vector of OB multiplied by F. So here I only have to find OB. So OB is, I want to go from O to B. First, I travel 4 meters in this direction, and then I travel 5 meters in Y direction, and finally 2 meters in negative Z. For I plus 5J minus 2K. And then you have to fill in the matrix IJK. And the first row is R component. These are 4, 5, minus 2. And the third row are the components of the force, 80, 40, minus 30. And here you have M1, you have M2, you have M3. And then you add them together. That is the solution. Did you follow the solution? Or do you want me to explain any part of it? Okay, I'll go to the next slide. Okay, last topic for today, that is moment of a couple. Moment of a couple is when two forces of equal magnitude but in opposite direction are causing a rotation. So this couple is simply the magnitude of one force multiplied by the shortest distance between two parallel lines. The shortest distance between two parallel lines is a line which is perpendicular to both of them, that is D. So here the couple is simply F times D, and direction, in this case, that is counterclockwise, that is positive. So I could take the couple with a any arbitrary point of rotation, and that is one way of interpreting the couple. The couple, if you want to calculate a scalar fashion, you simply find the shortest distance between two forces. But if you want to do the vector fashion, yes, R is any vector. So here I have one force here, one force over there. They are equal. This is F, this is minus F. But then the position vector should not be necessarily the shortest distance. That could be any position, R. So this is point A, this is point B, and then your origin of coordinate system could be anywhere. R is simply RA minus RB minus RA, isn't it? R is equal to RB minus RA. That's, if you solve that triangle, this is what you get. And therefore, my couple M is equal to RB minus RA multiplied by F. And the direction of the couple, you can work it out by the right-hand rule. If you want to find the couple in a vector fashion, yes, take whatever r you want. It's not necessarily the shortest distance between the parallel forces. But if you want to do it a scalar, you do need to find the shortest distance between the two parallel vectors. If there are few forces, they each would cause a certain moment, and eventually you can add all the moments together. And then that resultant is equal to the resultant of the forces multiplied by the position vector of the resultant. Here, someone is trying to grind the surface using a special tool. And here, the resistance of the grinder on the ground, that is causing a moment which is normal to the ground. Then the operator should apply a couple of opposite direction to cancel this one. If the operator doesn't apply that couple, then the grinder starts to rotate. The handle would rotate as a reaction. So here you have to find out, given that the distance between the handle, right hand, left hand are fixed, you have to apply a force which results in the equal amount of the couple with the resistance of the friction on the ground. In another word, MC should be equal to the force you apply and the distance between the shortest distance between two parallel forces are fixed. So the operator would hold the handles and he exerts two forces of equal magnitude in opposite direction. And this resistive couple cancels the frictional couple which the device applies on the ground. So here, let's replace the forces with a couple. The first one is the shortest distance we have is 150 multiplied by 0.4. And we know that normal to this plane, where the two parallel forces are, the normal to that is x direction. So the magnitude is 150.4, but the direction is positive I. In the second case, the two equal forces are 125, and the shortest distance is 0.3, but then the normal vector to that one is the one which is shown in this line. And that is sitting inside the ZY plane. It has a component of 4 along the Z, 3 over the Y. So you can write the unit vector of that one. The magnitude of this couple multiplied by that unit vector. You can describe the couple of AB. You can find the couple of CD, and finally you can add them together. The reason I'm going through this a little bit fast is in the exam is less emphasized on the three-dimensional case, but you always have answer to the solution, the detailed solution. The slides are available. You can download and use them. Okay, this is the last topic we have for today. So please listen this carefully. If you understand, if you listen once, you could understand it clearly. Here, I mentioned this at the beginning of the class, and I think that was Porty who mentioned a force can be transferred along the line of action. So in another word, this is an equal sign. It is okay to take this force, and this is the line of action. I can bring this force anywhere I want, here, here, and even there. So here, I transfer the force along the line of action. So this is okay. No penalty. If you change this free body diagram, this force to this one, you won't be penalized. No penalty for that. Everyone can live with this. Can you visualize? Can you accept it? Just take this as a recipe. A force can be shifted along the line of action without no penalty, with no penalty. That's what this figure says. Okay, but what happens if I have a force, and then is this okay if I shift this force from here, bring it here? Is this okay or not? Yes, no. Come on. All I ask is a yes or no answer. All right. Nguyen reckons we can bring that. And then Nguyen, if I bring, should I pay a penalty for that? Or is this without penalty? Nguyen, forget about all mathematics. Imagine that you are holding a wood, and then you put a heavy pot here. You feel much strain in your wrist, don't you? Because this is far from the point that you're holding it. In other words, your system has a high rotational tendency because of this distance. And then if I take that heavy pot and put it here, your wrist would be much more comfortable, isn't it, Porti? Nguyen. Okay? All right. So what I'm saying is these two are not equal. If I bring force here, these two are not the same system. So I have to pay a penalty. Then the penalty is I bring the force, and the penalty is a moment should be added to that. So this moment is the extra strain you had on your wrist when this was at the end of the beam. So I just said that in a pictorial way. The first one is if you shift the force along the line of action, no penalty. But if you shift the force normal to the line of action, so this is the line of action, so you are moving that normal to the line of action, you have to pay a penalty. How much penalty you pay? You have to add a moment which is equal to the how far you transfer this one, F multiplied by D. And then it is easy to prove that. The proof is, let me starting from this figure. I put F minus F here. So these two, they are doing nothing because they cancel each other. Okay. So in this figure, left-hand side, I added two forces opposite direction of equal sign. They don't cause any rotation. They don't cause any motion. So that is okay. No penalty so far. And now I just bring this one here. And these two forces are making a rotation. That hook is F multiplied by D, F multiplied by D. So that explains why the left-hand side is equal to the right-hand side. So in another word, I'm saying that, look, this system is equal to this system, which is equal to this system. All right. Everyone happy with this? That is the rule. We want to use these two rules to the next problems. Next problems, I'm going to shift a force first along the line of action, no penalty. But if I shift the force normal to the line of action, I have to pay a penalty. All right, so let's take some example of this. All right, here we want to find the rotational effect with respect to point A. All right, we want to bring all forces to point A. How can it be done? Just I'm using the two simple recipes which I just told you. The simple recipes is the force can freely be shifted along the line of action, but if you want to shift this normal to the line of action, you have to pay penalty. So let's apply this to this problem. So this problem is I want to bring all forces to point A. How this can be done? So question, Nguyen, is this okay if I shift 100 Newton to point A? Should I have to pay a penalty? Yes, you could, because 100 line of action is here. It is free to move that along the line of action. So I would cancel this one. That can be easily brought here, 100. So one step, I got rid of this one. How can I get rid of this one? Or let's get rid of this one. I want to bring 600 to here. How can I do that? So first, I bring this 600 to here. Should I pay a penalty for that? Nguyen? This is along the line of action, no penalty. I bring it here. And then I want to bring 600 from here to there because I'm moving that perpendicular to line of action. This is line of action. If I want to bring 600 to here, yes, I bring 600 here, but then I should pay a penalty. The penalty is 600 multiplied by 0.4. So this way, I got rid of this one. The last one, I want to get rid of 400. So let me bring that into two components. F, Y, and Fx. Okay, so how can I bring Fy to here? So first, I bring Fy here, no penalty. And then to bring Fy here, I have to pay a penalty. That is Fy multiplied by 0.4, 0.4. And how do I bring this force to here? First, I can bring that here with no penalty, Fx. And then to bring Fx to here, the penalty I have, I bring Fx here. The penalty I pay is Fx multiplied by 0.3. All right, so now I manage for one rigid object to shift all the forces into one single point. So this system has been simplified from what it was. So I started with this one, and then I ended with this simplified figure. So the very same shape, all forces and moment at one single point. 60 here, one moment, 60 times 0.4 here, 100 here, and one moment here, and Fy here, one moment here, and Fx here, and one moment over there. So all the driving forces, moment forces have been shifted to one single point. Okay, so that is the introduction to find out whether a structure is at equilibrium. It's very convenient. Instead of having the forces distributed everywhere, we can bring all the forces to one single point. And in that single point, you remember in energy and motion, we have the particle equilibrium. How a particle is at equilibrium? A particle is at equilibrium if the net forces are equal to 0, net forces vertically equal to 0, and net rotation are 0. That was for a particle, right? So this particle, no matter how many forces, moments are here, their net value should be 0. So this is an introduction. If you want to solve a structure for equilibrium, what you do is you find out the effect of all external forces into one single point. This becomes like a particle. And now this particle, you can apply three conditions. Condition 1, condition 2, condition 3. By applying these three conditions, the entire rigid body, this is not a particle anymore. This is a rigid body. Now you can find how a rigid body remains at equilibrium. Okay, so today we start with the new concept of moment, and we presented two techniques for finding the moment. The first one was using a scalar method, and the second one was method of vectors. And then we introduced the concept of the couple, and then we learn how the forces inside the system can be shifted into one single point. All right, so now for today, I put the name of Darcy and Flynn, Porty, Nguyen, Daniel, Abdullah as present. Okay, so that is all we had for today, and I'm taking any question you might have regarding today or previous classes. Okay, no question. Thank you very much, and I see you tomorrow in the AGSE 109, 10:30 to 12:30. So see you tomorrow. Thank you for coming to class, and I look forward to see you then. Thanks.